if we take 3 over 5, so in our previous picture we have this. We have, what did we have? What do we have on here? 15 and 9 here, right? Let's see if that works. If I take 3/5 on delta TA is 15 here. 3/5 of 15. 9. Okay, that's 9. That's that 9 here. Okay, so time is not universal. Okay, time depends upon the observer. So first I'll describe for you, to remind you sort of in physical terms what it is we had discovered, and then I'll show you that there's some very interesting geometry behind all of that. Okay, so here is Alice's space. So, and Alice is at rest in her space. And here's her clock ticking away, and here's her spatial axis. And she can see things happening in her space at various times according to her watch. Okay, so she can see various events happening. So an event is something that happens at some point in space at some time. So that's an event. So it happened at this location in space at a certain time. And here's another event happening at a different location in space at a different time. Okay, so let's suppose we just put those 2 events in Alice's space-time. So the first event was over here, and maybe it occurs at this time. So at this location, at this time, is an event. Okay, and then a little bit to the right of that, a little bit later, is another event. So a bit to the right, and a little bit later in time, is this event over here. Okay, so for Alice, those 2 events happen at different locations in space. One of them is here, and one of them is there. Okay, so there's a spatial separation between them, and there's also a time separation between them. Okay? Now, if I have 2 events happening like that, like this and this, you can imagine that there is someone walking in Alice's space, drifting through her space at a constant velocity, such that those 2 events happen at the same location for that person. Okay, so this person is drifting at a speed such that when this event happens, he crosses that location, and then he drifts across, and then this event happens, and he crosses that location. Okay, so from Bob's point of view, the first event happens right here at this microphone, and the second event happens right here at the same location. Okay, so it's always possible then to find a Bob. If we've got 2 events like this, it's always possible to find a Bob that will connect those 2 events. Okay, so here is the Bob. The Bob is just this one here. Okay, so for Bob, these 2 events happen right on his world line, right at his location, at 2 different times. So this event happens first. He's watching his clock tick, 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 tick. Then the second event happens. Okay, and so the space between those 2 events, okay, during that time, his clock is ticking away. Okay, and what we had discovered is this sort of thing. We had a triangle like this, and we had, suppose that between those 2 events, a certain amount of time elapses for Alice. She says, oh, an amount delta TA elapses for me. So since we're plugging C, speed of light times TA, the length of this side in meters will be C delta TA. And Alice says, well, the separation in space, the separation in distance between those 2 events is this distance here. Delta SA. And for Bob, the amount of time elapsed for him will be delta TD. It'll be different from delta TA. And we're calling it C times TD, so it'll be C times delta TD. Okay. So that's sort of the physical picture. If we have these 2 events, we can always connect them, provided that the events happen far enough apart in time such that a light signal could go from one to the other. Then it's always possible to find a Bob that will connect those 2 events, for whom those events happen at the same location. And then the time elapsed for Bob, we discovered, is a time dilation. So if this is 10 seconds for Alice, this might be less. This might be 9 or 8 or 7 seconds for Bob. Okay, to figure that out, what do I put here? How is delta TD related to delta TA? Not K. K is in this situation. So K is, if I have CT here, it'll be K from CT. Okay, so if I have a 45 here, what we've got here is a 90. And we've got this 90 here. So we're taking this total distance here, this one. So this time is related to this time by K, but this time is related to this time by what? Okay. Yeah, for your model, okay, so if we have a white triangle like this, then on this hypotenuse, the time elapsed on the hypotenuse is related to the time on the opposite side here by this factor, square root of 1 minus b squared over c squared. So this is the time dilation factor. So that time dilation is K is Doppler. And that K is 1 plus the square root of 1 plus over c over 1 minus over c. Okay, so this might be different. Okay. So that's sort of the physical situation. And we've got the physical time for Alice, her clock, and the physical time for Bob on his clock. Okay, but now, what I claim is that there's some geometry underlying this picture. I've got a triangle there, and I might have some kind of geometry associated with this triangle. So let's try to play around with this formula right here to see if we can discover some geometry lying inside that. Okay, so what we'll do is we will square both sides of that equation first. So the left-hand side is c squared delta td squared. And when I square the right-hand side, the square root disappears. So I get a 1 minus d squared over c squared times c squared delta ta squared. Okay, so what? Well, let's look at this v. What is this v? Velocity is distance over time. What is the distance in this case? delta xa. That's right. So Bob is drifting across Alice's frame, and he covers this much distance in that much time. Okay, so the distance is delta sa, and the time is delta ga. The distance that Bob moves in Alice's space divided by the time that it takes him to do so in according to Alice's watch. That's what he is. Okay, so let's just plug that inside there. Okay, so what do we get? We get 1 minus, I'm going to equal d divided by d squared, the square root of this I divided by c squared. Okay, so there's the d squared, and I also have to divide by c squared. And then I still have the c squared, and the ca squared. Okay, so now if I just expand the bracket here, the first term is c squared delta ga squared, subtract what? Delta xa squared. Okay, and so that's c squared delta ga squared. Okay, that's a very important relationship. So that's the relationship between the squared lengths of the three sides of that triangle. Remember that because we're plotting c length times time, everything is, this is measured in meters and so is this. So space and time are both measured in meters. Everything's measured in meters. So meter squared equals meter squared minus meter squared. Okay? So there's some relationship between the squared lengths of the sides of that triangle. So let's just simplify that expression. Okay, so let's call the time according to Alice A, the distance according to Alice D, and the time according to Bob C. Everything measured in meters. What is this thing telling me? How do I express this equation for A, B, and C? C squared equals. So, does that look right? Not quite right, right? What's that minus sign doing there? Go away, yes. Okay, so let's just do a simple example here. So, for example, suppose this side were 5. So 5 meters according to Alice on her clock, and Bob had drifted a distance 3 meters between those two events. What is that? What do you think that means? 4. If we go 5 squared is 25, minus 3 squared is 9, is 16, square root of that is 4. Does that look right? Okay, like it's saying that this side is shorter than that side. How could that possibly be? Yeah, I think it's because on the height, if you compare the 4 and the 5, like the distance between 1 second and 2 seconds, the 4 is much longer than the 5, so that's why you have up to 4, and then the 5 is not because it's time dilated. Yeah, so it's time dilated this way. So the fact that this is shorter than this is precisely because of the time dilation. So we know that if 5 seconds elapses for Alice, then because Bob is moving out with Alice will look at Bob's clock and see that less time elapses, time is running slow. So this clock has to be slower than this, based on just distance. Okay, but mathematically, we're not used to that kind of situation. Yeah. So you can imagine a component outside thing, so somehow will shape and yeah, so that's a great idea. So the suggestion is that maybe there is some kind of geometry here, except it's not just geometry on a flat plane. Like for example, suppose I have a sphere like this, and I have 3 points on this sphere. When I connect these 3 points, I'd like to connect them with straight lines. Well, of course, the sphere, so from the outside, I can't really connect the straight lines. I have a curve, get to the curvature of the sphere. Right, so a straight line might be the shortest distance. What's the shortest distance between 2 points on the Earth, on the globe? Geodesic, right? So that's the path of the plane takes. Okay, so that path might look something like this. I mean, let's see if I can on the equator. Here's the equator. The equator is an example of a geodesic section of the equator. The triangle might look like that. Okay, so if I draw a triangle on a closed surface, on a flat surface, the sum of the interior angles is what? 180. What does the sum of the interior angles look like here? Bigger than 180. Right? Let me actually draw that. That's pretty obvious. Let's take the top one to the North Pole, and 2 points on the equator. And these arms are just lines of longitude. This is on the latitude of the equator. What is this angle? What is this one? Okay, we've already got 180 here. What's this? Okay, so if you draw a triangle on a curved surface, you'll find that, there is a geometry, still a symmetrical thing, but it's not the usual laws of geometry. Okay? In this case, some of the angles are bigger than 180. So this is a similar sort of thing going on. We have a triangle. There is a geometry. Okay? We have some kind of relation like this, which looks like Pythagoras, but it's not quite the same as Pythagoras. It's not Euclidean geometry. It's a different kind of geometry. So it turns out that this kind of geometry is still flat, but in a weird sort of way. Okay? So this kind of geometry is called Minkowskian geometry. So if we had c squared equals a squared plus b squared, that would be Euclidean geometry. But we have, so this is in a two-dimensional space. In a two-dimensional space-time, one space, one time, it's c squared is a squared minus b squared. Okay, and just a tiny bit of history here. So Einstein had come up with this sort of physical picture of what's going on. He was the first to properly interpret what this this whole time dilation idea. And then one of his professors, his name was Minkowski, looked at what Einstein had done and realized that, hey, underlying the physics that Einstein was talking about, there is a geometry. So now this geometry is called Minkowskian geometry. Okay, so it's distinguished from Euclidean geometry. Okay, so yeah, right. Okay, so let's look at 2 examples here of this interesting kind of geometry. Okay, so first we'll look at Euclidean geometry. So we'll take 2 points called an alpha and beta. These are 2 points in space. Points in a 2-dimensional space. Okay, so 2-dimensional space, what we mean by that is we have a coordinate system. Say that this is a flat 2-dimensional space, the space of the blackboard, and we put some coordinate system on it, x and y. And let's measure both x and y in meters. And we have 2 points in this space. Say one of them over here, and say one of them over here. Alpha and beta. And so someone is taking a trip, say, from here to here, and suppose that there's many ways to get from alpha to beta, but one way is just to take a straight line path from there to there. Okay, another way is maybe Alice takes this path from here, and maybe Bob takes this path instead. He goes up to here, visits someone over here, and then continues his journey up to this point beta here. Okay? So let's just look at some numbers as an example. Okay, so suppose that the distance here is 3 meters or kilometers, whatever we want to use, and this is 4. This is 4. So what are these sides? Okay, so we would find these sides by saying, well, this side length is the square root, according to Euclid, the square root of this squared plus this squared. And similarly, I have a right triangle here, so I go square root of 4 squared plus 3 squared is 5. Is 10. Okay, so what we have is for Bob here is 10, whereas for Alice the distance is only 8. So 10 is greater than 8. Okay, so when we look at that picture, we say, okay, let's measure this in kilometers. Okay, so we got these 2 points, 2 cities or whatever, and Alice takes a straight line path, and her odometer reads, 8 kilometers to get there. And then here's Bob. Bob takes a detour like this and comes back, and his odometer reads 10 when he's done. And so when they get together again, they both leave with their odometer that reads 0, and they take different paths to get from there to there. When they get together again, they compare their odometer and they say, oh, my odometer reads 10, oh, your odometer reads 8. But it's not like a big deal, right? They just took different paths, right? Okay? So that's easy. Let's take an exactly analogous situation, but in Minkowskian geometry, space-time. Okay, so now what we do is we have a space axis and we have a time axis, actually c times t, and maybe this is space and time according to Alice. Okay, so now we have a situation like this. We'll pick 2 points in this space-time. So this is alpha. Okay, so these are points in space and time. So maybe the point in space we were talking about is Earth, and the point in time is now. So this is Earth now. And the point beta, you see it's the same point in space, so it's the same point on the Earth. So it's beta. Same point in space, but it's later in time. So it's Earth then. Okay, so we've got two events. The first event is here and now, this event, and then we wait a while. The second event is this event, which is the same place but a later time. Okay, so Earth now, Earth then. Okay, and there are lots of ways to get from Earth now to Earth then. One is to go like this. Here's Earth now. And here's Earth then. The one is just do nothing, stand there. Okay, so this is the Alice's path, just standing there. Okay, she doesn't move into space. She just moves in time. But now there's another way to get from here now to here then. I go here now, and then I run over here, and I run back. I'm still here, but later. Okay, so that's this path. Okay, I run over there, some distance away, and then I run back. Okay, so let's see. We've got 2 right triangles there. Now let's just put some numbers on here. Let's measure both of these in meters, or more use meters here. Okay, and so we say, suppose this is 5, and this is 5, and this is Alice's path between alpha and beta, that's Bob's path between alpha and beta, and suppose that he ran to a distance of 3 meters, and then runs back, so that's 3. Okay, so what are the lengths of these sides? Okay, so we use this Minkowskian idea. We take the square of this side is the square of this side minus the square of that side, and then square root. So 25 minus 9 is 16, root of that is 4, and this is also 4. Okay, so we see, for Bob, the total autonomy mass is 8, whereas for Alice, it's 5 plus 5 is 10. Okay, so if we compare these situations, first of all, there they're identical in the following respect. They're identical in that, basically, Alice, in going from alpha to beta, she is measuring her time. Okay, so rather than using an odometer, so in this picture over here, Alice and Bob have an odometer in their car, and that thing rolls. As they're covering distance in space, that odometer rolls away and reads out how much distance is covered in space. Okay, instead of an odometer here, in this picture you have a clock. Okay, so Alice has her watch. Her watch rolls around and measures her distance in space-time. Okay, it measures the elapsed time here from there, and that's 10. Okay, and Bob does the same thing. Bob's got his clock. As he's walking over here, his clock is rolling like this, just like an odometer. His clock rolls all the way back, and then when he gets back, he looks and finds, oh, my clock reads something 8 compared to your clock, Alice, which reads 10. Okay? So they're exactly the same. And one way to sort of say this is basically a chronometer, just an old-fashioned word for a clock, is space-time odometer. Okay, so what your watch does, as you're walking around all day, your watch is like clicking away, tick, 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 tick. What your clock is doing is it is measuring the distance that you cover in space-time. Okay, so another example, let's say this. So suppose that you stay in the room here, okay, and so here's your space-time odometer, there's your clock just ticking away. And then I go away and I walk around the building, I do all kinds of stuff, and I come back. But while I'm walking around, I'm covering some distance in space-time using this Minkowski geometry rather than this usual Euclidean geometry. Okay, but the distance that I cover this is exactly the same thing. So my clock is recording the actual physical distance, the geometrical distance in space-time along that path. Okay, so that's all the time is. That's exactly what time is. Okay. So if we look at this, if we look at, say, the famous twins paradox, okay, so the twins paradox, that's exactly what this is, right? So what we're doing is we're saying, say, here is Earth now, and here is Earth later, and suppose that there's a planet here, far away. This is the world line of the Earth. This is the world line of the planet. It remains some fixed distance away from the Earth, and say it's 3 light years away from the Earth. Okay, and then so Bob takes a trip over to that planet, and then he comes back. Okay, and so we say, suppose it's 5. So Alice says, oh, look, it took Bob 5 years to get from here to that planet, and then 5 years to get back. Okay, so 5 years, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So a total of 10 years has elapsed for Alice. But for Bob, there's this time dimension happening here. Okay, so we 1, 2, 3, 4, 5, 6, 7, 8. So a total of 8 for Bob compared to 10. Okay? So there's nothing mysterious about that. Are you okay with that? Does that make sense? Well, here's what I'm moving to. So here we've taken the point of view that Alice is at rest, so we're mind vertical, and there's Bob, yeah, moving away and coming back. But now we can try to take the point of view that Bob is at rest. So let's take the point of view that Bob is at rest. So Bob is in his spaceship, he's at rest in his spaceship. He sees Alice drift away, he gets to the planet and turns around and sees Alice in the water. So now we can take the point of view that Bob is at rest and it's Alice. And then why wouldn't it be just the reverse? Why wouldn't it be only 8 years for Alice and 10 years for Bob? You see the problem with that? Coming back to Bob, in that with all the point of view being stationary, then you're going to have to take a steeper angle, and the angle is going to be the center. So what's the concept? But I don't know how people pull that up. Well, let's try to do it. Okay, so how are we going to do this? So Bob is at rest. Right there. We're going to get Bob is at rest. And then what do you see? You see Alice going away in the other direction. And then still Bob at rest. You see Alice going back like this. So this will be the reverse picture, and we say, oh, well, okay, so it's only 4 and 4 for Alice. I'm going to 8 for Alice. So that's at least 10 for Bob, and it's reverse. So why can't I just do this? Why can't I just do that? Yeah.
Well, because you're assuming that in order for Bob to go from there to there, but in reality, it has to accelerate his way in the reverse direction, and then therefore the special relativity works differently, and therefore he can't do that.
Okay, so I agree with you, absolutely. So there are 2 reasons why we can't do this. One of them is physical. Okay, so in this picture, this is a straight line. Okay, and so it means that there's no acceleration. Moving at a constant velocity, in this case, 0. Okay, and this is also constant velocity, but when we get to here, it's actually there's some acceleration. The line bends here. Okay, so Bob has to change his velocity from moving to the right, moving to the left. So he has to slow down, stop, turn around, and pick up speed again. So he has to accelerate. Okay, so at this point over here, Alice feels absolutely nothing. It's just, the usual day, right? Here, Bob, he spends his whole day like super braking, and super accelerating back. Okay, so he's well aware that something is happening here, even though all the windows are closed and everything, right? Okay, so there's something physically different about that. So we can't simply do this with this. These are not equivalent, because it's in this picture that Alice is accelerating and Bob is